2, 1, welcome back. All right, so the first probability test that I'm going to go over. So this one, it doesn't have many questions. There's about 5 questions, but I think the questions are worthwhile. All right, so as typically when I do the tests themselves, I'll put up a link up down in the show notes so that you can download the PDF version of the test, try it out on your own, and then come back and then see the solutions. All right, and if you have any comments, you can put them down in the comment section. Okay, so let's get started with question number 1. So for question number 1, I have set up kind of a different version of the poker probabilities, okay, which uses combinations quite a lot. I did an entire series of every single thing that happens in poker, the 5-card poker, which is the standard poker. This one, I called it short poker. There's only 3 cards that you draw out of 24 cards, which starts from 9 all the way up to aces. And if you want to see the full out, all the videos with regards to poker, I put up a link up above there to the video playlist for that. Okay, so now coming back to this question number 1, let me first paste it in here. And so we have 2 parts. So as I said, we're playing this kind of new poker, which is short poker. You're using from 9s all the way up to aces. So that means you have 24 cards in total. So 9s, 10s, jacks, queens, kings, and aces. So 6 times 4 is 24. Then the game of the short poker involves just drawing 3 cards, so instead of the 5. And now they ask you for 2 things. So for part A, what is the probability of drawing a straight? And we're going to exclude the straight flush and I guess the royal flush, which would have been just 4 of those if it was just queens, kings, and aces. All right, so let's take a look at this one. So I'm going to go about it in the following way. All right, so we want to have a straight. Okay, we have 3 cards, okay, that we're drawing right there, and we're drawing from, this is 9s, 10s, jacks, queens, kings, and aces. Okay, so now a straight is basically you have one of the following. So you either have a 9, a 10, or a jack. Okay, we're going to exclude the straight flushes, so they can't be of the same either hearts or diamonds. Okay, so they have to be of a different kind in there. Then you can also draw a 10, a jack, and a queen. A jack, a queen, and a king. Okay, or a queen, a king, and an ace, right? So we can draw 4 different types. And so what that means is the following. So there's 4 different ways of drawing this, right? So this is 4. So as I said, 9s, 10s, jack, 10, jack, queen, and so on. And now out of those, okay, so notice that each card, so if I draw a 9, so let's assume that we would draw 9, 10, and jack. So this, or this. Now I have 4 9s to choose from, right? So the first one, this is going to be 4, choose 1. Okay, let's say if it was just 9s. It can be, 4, choose 1 if it was 10s, because there's 4 10s, and then 4, choose 1, okay, if it was a jack. And now I have 4 different kinds of these, because I can now also say that this is 10, jack, and queen, and so on. So this is going to be 4, choose 1, okay, to the power of 3, because 1, 2, and 3. All right, so those are all the straight flashes, all the straights that I can get. Now I have to exclude the straight flashes. So in terms of excluding the straight flashes, what would I have? So that's a straight. Now a straight flush, what would that include? So I have again 3 cards, but they have to be 9, 10, and jack, and then the suit has to be, okay, so kind and suits. Okay, so we have to be careful there. Okay, so what would it be? Well, we still have 4, so we can have a 9, right, 10, and a jack, a 10, a jack, and a queen, a jack, a queen, and a king, and then the last one, queen, a king, and an ace. So let's say if it was a 9, you know, a 10, and jack. So basically we have, again, 4 of those to choose from. Either starting from a 9, starting from a 10, starting from a jack, and starting from a queen. But now I don't have, you know, 4 choose 1 for every single card. I only have, you know, 4 different, so diamonds, you know, hearts, spades, okay, and clubs. So those are only 4 choose 1, okay, that I will have in total, okay, for each individual one. So those would have been all my straight flushes that I would have. Now I have to exclude, okay, those, so it's going to be 4. Notice I have a 4 for both of them, so maybe I'll take it out. So I have a 4 and a 4. Okay, so this is going to be 4 choose 1 minus, okay, this 4 choose 1. Put all of that in brackets. So notice I took out the 4. And they are asking me for the probability. So probability means this is going to be all over. Now I have 24 cards. I'm going to choose 3 of them. So those are all the possible ways that I can choose my cards. And these are the cards, all the possible ways that I can choose a straight, excluding the straight flushes. So now I can calculate what that probability is. Okay, so you can set it up, you know, and then find out exactly what that is. So I'll leave that up to you, okay, because that is just computations. So this would have been 4, you know, and then in brackets you have 4 choose 1, which again is 4 cubed. So 4 cubed minus 4. Then do the multiplication and find out 24 choose 3 at the bottom there. Okay, so that's part A. How about part B? What are the odds of drawing a pair? Okay, so this one is a little bit different. So drawing a pair, and now they want the odds. So we're going to have to find out the odds instead of the probability. Okay, so again, I am drawing 3 cards. Okay, I'm going to separate this one. But I want a pair. All right, so between the 9, the 10, okay, the jack, queen, king, and an ace. So, you know, how many pairs can I draw? Well, I can draw a pair of 9s, right? I can draw a pair of 10s, you know, jacks, queens, kings, and aces. So that is 1, 2, 3, 4, 5, 6. So I can have 6 choose 1 of them. All right. So either a 9, a 10, a jack, a queen, king, and an ace. So that's 6 choose 1. And then multiplied by, now once I pick one, so let's say I picked the 9. Well, there's 4 9s that I have, but I need a pair. So it's going to be 4 choose 2 that I'm going to pick inside there, right? So those are all the possible ways, okay, that I can have those pairs. But that is also going to be, so now here I still have one more card. Now I'm not going to be choosing 6 choose 1 out of here because I picked one already. So it's going to be 5 choose 1. So it's the remaining ones that I want to choose from. And then this is going to be multiplied by, because let's say the pair was 2 9s. That means this can be a 10, a jack, a queen, a king, or an ace. So that's why, so there's 5 choose 1. And then of course there's 4 of each one. So 4 choose 1 of them that I would have. And all of this has to get multiplied to try to figure out, how many pairs, okay, or, one single pair can I draw. So that's how we would do that. Okay, but now they want the odds, so I have to figure out what this is. So I'm going to just compute this. Okay, I'll do it in fast forward fashion here. All right, so there you have it. So that's the total number of these pairs that I have. So there's, a few of them, but we're only drawing 3 cards. So it's not going to be as the regular 5-card poker where you have quite a lot of different combinations. Okay, so since I want the odds, I need to know, so 24 choose 3, right? Because the odds are going to be, so 7, 20, 2, so this is for drawing a pair versus not drawing a pair. So I need to know all the different types, okay? Now 24 choose 3, I guess. So that's 24 factorial, and 24 minus the 3, so 21 factorial and 3 factorial. All right. So, well, that's going to be gone. So 24 times 23 times 22 all over 3 factorial, which is just 3 times 2 times 1. All right, let's simplify this. It's 11, 3 goes into that, 8. And then, so my answer, that's going to be the total number. So 8 times 23 times 11. So that is the total number of those. All right. So 2024 minus 720. 2024 minus 720. 1303. So those would have been my odds. All right. So there you have it. So that's the first example that we have. All right. Okay, so this example, we're going to take a look. So it's a probability example. So there's a hospital and it's faced with fighting several virus strands. So the hospital currently has 1,215 patients. Okay, so let's write down these givens. So total is 1,215 patients. A total of 73 patients have the alpha strand virus. So we'll put, so alpha strand virus, so that's an alpha there, 73. There are currently 60 patients who are carrying the beta. Okay, so there's 60 right there. Let's write that down. So 60. From the beta strand carrying patients, 25 of them also have the alpha strand. Okay. So that means that we have beta and, okay, they have alpha, and there are 25 of those. So we can try to do kind of a Venn diagram to illustrate this as well. We probably don't need the Venn diagrams to solve these, but in any case, so let's say if this is alpha, this is beta, we'll make it, here's their total there. So we have 1, 2, 1, 5 in total. So there's 25 in there, which means so 60 minus 25, so 35 in there. And then we have 73 minus the 25, so 53, 48. Okay, so I think we have that. All right, so we'll see if we're going to need that or not. But okay, the question is, if a patient is selected at random, so this is important, so we just pick a random patient, then what is the probability that the patient has the beta strand virus? Okay, well, probability of beta strand, so this is for A, so that's not very hard because they gave that to us. We have 60 all over the total if we're choosing at random, and you can calculate what that is. I'll leave that for you if you want to switch it back or reduce the fraction. So that would have been part A, so that's not bad. Part B, the patient has either the alpha or the beta. Okay, so probability of alpha or the beta. So that means this is going to be probability of alpha plus the probability of beta, but of course we have to subtract that intersection there, so we don't count them twice. So this is not mutually exclusive because they're sharing that. Okay, so we have this, but we can also pick that out, for choosing, if this Venn diagram actually does the job, because we can count everything up. So 48 plus 25 plus 35 all over 1, 2, 1, 5 would have given us the answer. Or you can do this, right? Which is going to be, so probabilities of, so they're all over 1, 2, 1, 5. Probability of alpha, so 73 plus 60 minus that 25, which would have given us exactly the same thing with regards to those. Okay, so what does that equal? You can add it all up and then find out what the answer is. So 73, okay, we can do that. 73 plus 60 and then minus the 25, so that's 108. Okay, so 108 all over 1215, and again, you can reduce this if you like. I mean, I guess I can kind of cheat here because my calculator will reduce that for me. Let's see. So, okay, so that's a nice 4 over 45. Okay, right there. And as I said, you could have said 48, plus the 25 plus the 35, and it's going to give you the same thing, 108, and then all over the total. So that's part B. So one or the other. Part C, the patient has the beta strand virus, but not the alpha strand. Okay. Well, from the Venn diagram, so that's relatively simple, right, to get, because if we're only looking for beta, so that would have been 35 and then all over 1, 2, 1, 5. So you can use that. But I'll also kind of remind you when you're doing this, because if you're talking about sometimes conditional probabilities, so notice what they want is, I think they said beta, right? Yeah, beta. Okay, they said, so we have beta and not alpha. So not, I'm going to put not, kind of that, all over. So this, with you utilizing conditional probability, so this is the same thing as saying probability of beta, so that means, probability of having the strand. And then if you know that they have this, then you multiply it by the probability of not alpha given that you have chosen, okay, or you already know that you have beta. So this is actually going to give us the same thing. So from the Venn diagram, right, it was 35, 1, 2, 1, 5. So very quick. You can use that. But this also will give you the same thing. So probability of beta, so that was, I think this was 60, right? 1, 2, 1, 5 multiplied by this conditional probability is, so given beta, so that means this is over 60, okay, because we know that there's only 60 beta, and not having, okay, alpha, so that means it's this, all of these guys right there. So this would have been 35, and notice these cancel and you get exactly the same thing. A little bit more work, and again, you can reduce this if you like. Okay, so that would have been part C. Now part D, are the patients with alpha and beta strands mutually exclusive? No, they are not. Actually, I already said that. They're not mutually exclusive. If you need to have mutually exclusive, that means these would have to equal 0, but this is not 0, right? So they do intersect. So the answer is no, they're not mutually exclusive for that. All right, so that completes another nice probability example that you can use Venn diagrams or some conditional probabilities. Okay, that's it for this one. All right, so this is another probability example that we're going to try to use. It does use conditional probabilities within here, and it's kind of also independent events. So it is a combination of the two which we can utilize to solve this problem. So it says JD can consistently obtain a mark in the 80% range with a probability of 90% when his confidence level is high. Okay, so let's write down these givens. I just want to break all this thing down. Okay, so when his confidence level is high. Okay, so confidence level is high, and he can obtain 80, so the probability of obtaining 80%, I guess, plus is equal to 90% or 0.9. When JD's confidence level is not high, okay, so when it is not high, so notice that the two are mutually they're independent, okay, so high and not high, okay, so they can't happen simultaneously at all. Okay, so we have now probability, and then he has a probability of only 30%, okay, so probability of obtaining this range is only 30%. Now, on any given day, the probability of having high confidence is 75%. Okay, so probability, okay, of high confidence is going to be 75%, which means probability of not high confidence, okay, is going to be 25% or 100% minus the 75. Okay, so what is the probability that JD will get a mark in the 80% range on today's test? Okay, so let's take all of these into account. So we want to know probability of 80% range. What is that? Well, it's going to be equal to, okay, so we have, I guess, probability of, okay, so on the day where he has high confidence, and obtaining, 80% range plus, okay, plus it's going to be the probability of low or not high confidence. I'm going to do that and trying to get that 80% range. Okay, so, well, what does this equal? Well, this equals to the probability of having high confidence multiplied by, this is from the conditional probabilities, so probability of trying to get 80% given that it's high, plus, okay, now the second one, this one, so probability of not multiplied by probability of trying to get that 80% range given that his confidence is not high. Okay, so now we're going to have to do this. So if you substitute all of these, now we know, so when it's high, so given that it's high, all right, so when does that happen? That happens with 75% multiplied by, now probability of 80 given high was 90%, so that's that. Okay, plus, so now the opposite, so 0.25 multiplied by, no, it doesn't do very well. Okay, so with 30% range or probability. Okay, so now we can compute these and obtain our answer. Let's do it. So that would have been the probability. All right, on any given day. Okay, so that's a great example and another one in the bag. Okay, thanks for watching this one. All right, so another birthday probability question. Okay, so what is the probability that in a class of 20 students, 2 or more have the same birthday? Okay, and we'll assume that there's no birthdays on February 29th, so we're not dealing with a leap year or anything like that. We could, it just means that there would be one more day in a year, but we'll just stick to 365 days. Okay, so we have 20 students. So the way that I'll set this up is the following, and you can think about this, okay, in this way. Now, the easiest thing to do with these types of questions when you're trying to find the probability of at least 2 or more is to do the opposite. Okay, so basically we want to get, okay, so 100% minus, okay, the probability that nobody has the same birthday. So nobody, okay, has the same birthday. So this is the way to approach it, because if you take 100% minus that, then that will just simply give you what is the probability of 2 or more, okay, having. So that negation actually kind of helps. So now, in order to set this up, okay, where nobody has the same birthday, we're going to line up the total number of students. Now, it doesn't matter how many there are, okay? So this is going to be, you know, student number 1, student number 2, student number 3, student number 4, all right, and so on, all the way up to 20, or, you know, the total number of students that you have in a class, or, you know, the number of people you have in a room, or whatever it is. For us, this is 20. And now, you know, you can start. Okay, so you can choose arbitrarily who the first person is, right? So they clearly have the same birthday as themselves. But, you know, once we bring in a second person, now we can say, okay, what is the probability that these two people do not have the same birthday? Well, it is, okay, so if this first person has a particular birthday, that means that the next person will not have the same birthday. That will be the probability, right? 364 out of 365 days. So it can't be on the same one. Okay, so that's the first person that comes in. So those are the two people that are in the room, and that's the probability that they will not have the same birthday. Okay, now as you add the third person, so that means the third person cannot have the same birthday as the first two, which means, you know, so that leaves that person with 363 days over 365, right? That's the total number. Now, when you multiply these two, right, so that's the multiplicative, okay, principle. So as we have that, that will now just give us what the probability that these three people do not share the same birthday. And we can continue this, and as you can see, 362, right, so that's going to be the next one. Okay, that's when the fourth person comes in. All right, and you keep just multiplying these through, okay, all the way. And then, you know, if it's 20, so I guess, so notice when you're subtracting, it's just 1. So it's not going to be 365 minus 20. It's going to be 365 minus 19, which I guess is 346 all over 365. But in general, it's 365 minus, okay, n minus 1. Okay, if this n is just an arbitrary number of people over 365, so you can keep that in mind. Now, this multiplication is annoying because there's a lot of them, right? So the more people, you're going to have quite a lot of multiplications that you will have to do, and it just gives you this. Once you have that, right, you can now subtract it from the 100%, right, or 1 if you're keeping it all. So notice I kept it as a fraction, so it's going to be 1 minus, you know, all of this junk, and you get what the probability is of, you know, 2 or more people having the same birthday, okay, which is kind of neat. So I'm going to do the calculation for you just so that you have it, but I'll do it in fast forward fashion. All right, so there you have it. Okay, so now, I mean, this I'll leave up to you. So it's around, you know, 59%, so about 41% or so, you know, the probability. Now, what you will find interesting is if you start moving this up, let's say if it was like 22, 24, very quickly this is going to go over 50%, which is kind of crazy. I think about 24 people you need, and it's going to be over 50, or maybe even 23, which is not that many. You wouldn't think that you would have, you know, it's basically like flipping a coin and getting heads. So if you only have about 23, 24 people in a class, you can get the probability up there. Okay, now the only annoying part is, and I hope maybe your teachers won't make you do this, is actually to calculate this on a calculator. Like, you know, you you saw I was fast forwarding the calculations, and it took quite a bit to input this in, and it's very easy to make a mistake. So, if I was a teacher, let's say, I would probably just do this, okay, and then I would accept that for full marks, just so that somebody can show me how to do that, okay, and set it up. All right, so that's another nice probability question. Thanks for watching this one. So a group of 8 sprinters are to race the final. Two teammates made the final. What is the probability that they will start beside each other? Okay, so it's a probability question within here. Okay, so we have, and it's true, I guess on a racetrack you typically will have 8. Okay, so 4, 5, 6, 7, 8. All right, so let's say this is the start line. So if we have 2 teammates, and we want to know what the probability is that they will be beside each other, so that means that you can do it in the following. So I guess we'll do permutations because order will matter, right? This is not like dealing cards where the order doesn't really matter how you receive the cards, but here the order does matter. So we have 1, 2, 3, 4, 5, 6, 7, 8 lanes. So the total number will be, I guess, 8 factorial, or 8 permutation 8, right? So these are equivalent. That's the total number of ways that we can rearrange these sprinters. Now, 2 of them are to be together, okay? So that means, we're going to group 2 of them. We want to know when they're going to be side by side. So we have that, and then we have the rest, okay? So it's going to be 2, and then 1, 2, 3, 4, 5, I guess 6. So that makes it 8 lanes, and these 2 guys are supposed to be together. So now instead of 8 factorial, we can rearrange these where this block is acting as 1. You can another way, this could have been here, right? So this just depends where they start. They can start line 1, 2, 2, 3, and so on. So except they're always together. Okay, now within here, you can arrange them 2 different ways, right? So the first teammate in lane 1, second teammate in lane 2, or vice versa. So there's 2 factorial ways of rearranging this. And then in total, if that block, now this is going to be 7 factorial ways in rearranging the 7 different blocks, the 6 individual sprinters, and then the 2 that are supposed to be always side by side. So I'm treating that as a block. So that's going to be the following. So the probability will be equal to, 2 factorial multiplied by 7 factorial divided by the total, which is 8 factorial. All right? So that's what we will actually have. And this is, I guess, going to be, 7 factorial. So it's going to be just 2 all over 8, which is a quarter, so 25%. That's the probability that they're going to be side by side. All right, and that's a nice example. It's not a very difficult one, but it brings you back to counting and trying to understand order in there. Okay, thanks for watching. See ya. Bye.